as just to give you some idea of what's happening. S squared S minus T squared minus ST. So the coordinate ring of this nilpotent cone, you can think of it as being generated by these quadratic polynomials S squared, ST, and T squared. So this is the same thing as C2 over the statement that we wanted to. Right, okay, so it's protein related. But this is very, very well studied, and this is kind of quite easy to understand. We've got two types of point inside this nilpotent cone. We've got the non-zero points, and all of those are smooth, and you can sort of check. You want to get the only non-smooth point in the origin. So we've got two strata. The orbit of a non-zero nilpotent and zero, right? And in general, the picture is like that, but much more complicated. So we have a partial order on the nilpotent orbits, which is given by the closure order on these things. And this is a really useful way to kind of analyze the nilpotent cone. I'm just going to write down some maybe over here. Keep this. Yeah, I feel like we have the same problem. This is the COVID cleaning stuff has ruined all the whiteboards. So you can't.
Oh, I didn't realize that was also the fault. I didn't realize that was also the fault of COVID. I thought we had this problem already before. I have to try to remember. Usually I used to have I have a product here that can make that better. If it's really bad, I have this spray.
Okay.
That will solve the problem.
So we've got the following orbits, just to write these down. These will need to be more in mind. But the first one is the regular orbit. This is the set of all, sometimes you see these called principal nilpotents. The regular means that the dimension of the centralizer is minimal. It's equal to the rank of the Lie algebra. And the set of regular elements of N are dense. So you have an orbit in here which is the same dimension as the dimension of N, which is the dimension of G minus the rank of G. So this is the regular orbit. Now, so this is the unique maximal orbit with respect to the partial order. Right, and so that's kind of not very surprising. We've got an irreducible subset, finite number of orbits, so there should be a unique maximal. And then what's perhaps slightly more surprising is there's always a unique one which is just underneath the regular orbit. That's called the subregular. So the subregular one is the dimension of the centralizer. In fact, I'm going to write the centralizer like that. It's equal to the rank of G plus 2. The subregular orbit. So in the case of SL2, subregular means 0. Right? And then we've got a load of different orbits in the middle, and then I'm going to leave a space. But we've always got what's called the minimal orbit, which is the orbit of a long retirement. Dimension of this varies, depends on the type of the algebra. And then we've got 0, right? So the partially ordered set of nilpotent orbits, the unique minimal element of that set is the 0, but that's kind of trivial. So we refer to the next one above that as the minimal orbit, right?
And this alpha hat, sorry, this means
so this is the highest root element. Any long root element will do.
Right. I see.
The highest root. Okay. Okay, so those are, and so if you write this post set as a Hester diagram, that means there's one edge of the problem, one edge of the top. Okay, there's something to say about these nilpotent orbit closures. So the smooth locus of O bar is equal to O, right? You start with a nilpotent orbit, take its closure, and the things that we accept as, those are all of the singular points of the closure. Right? So in general, these nilpotent orbits, the big contrast with the case of a semi-simple orbit, for example, an orbit of semi-simple elements is closed already, but therefore it's smooth. And so the moment you start having to add in extra points to get closure, things that you add at the boundary, those are the singular points. That's slightly complicated by this normalization picture. So what I said isn't quite true if you take normalization. Let's not linger on that too long. Okay, so what this means is, so for any nilpotent orbit O, I've got a disjoint union of orbits which make up the closure. And this partition reveals a lot about the singular structure. Singularity. Right, so in essence, so if you start off with a nilpotent orbit, and you're interested in studying the geometry of the closure, well, you contained within that, you've already got this partially ordered set of orbits which are less than, right? So, and it's a stratification. Now, when is this an isolated singularity? Well, it can only be an isolated singularity if you've just got O and 0. If you've got any other orbits involved, then they all sort of collapse down to 0. So this is only an isolated singularity if O is equal to O. Okay, so that's and that's called a minimal singularity. And following some seminal papers of Proctor Pachedi in the early 90s, we just used the lowercase letters a, n, b, and c, n to denote the corresponding minimal singularity.
But that's the same thing as an isolated singularity, though. A minimal singularity.
Sorry?
A minimal singularity is the same thing as an isolated singularity, then. Or you mean by that always the closure of a minimal orbit?
Yeah, it's exactly. It just means the parallel bar.
Okay.
Yeah.
Right.
There are other examples of isolated singularities.
Right.
I'm just going to, this is family number 1 of isolated symplectic singularities. Sort of well known from the very beginning, even before Bode had defined what a symplectic singularity was. There are 2 families of natural families of isolated symplectic singularities. This is one of them.
So how far back does it go?
Does
you say it's been well known. So I know for work by Joseph.
Yes, I was going to mention Joseph. So you've got this relationship with the University of Pennsylvania, right?
As soon as people were studying, as soon as people were studying orbits in the nilpotent cone, and
Yeah.
but I guess the thing is that technically also this is not always a symplectic singularity by Bourville's definition, because these don't have to be normal, right? These omen bar.
So these are
On A and B and C and anyways, I guess, but always normal
the minimals.
for all types.
Mm-hmm. Yeah.
Okay.
Not special.
Oh, I see. Okay.
Okay.
All right. It's always normal. Okay.
So the second family.
Sorry, could I ask
The Kleinian singularities that we know are subsets.
I was just about to, are they, no, so these are dimension, so dimension here is greater than 2 except for A1. The minimal singularities are arbitrarily large dimension. There's a formula involved with the Coxeter number, twice the Coxeter number or twice the Coxeter number when it's 1 or something.
Yeah, -2.
Yeah, -2. Yeah. So the second family of symplectic of isolated symplectic singularities is exactly as you said. It's the Kleinian singularity. So there are lots and lots of names for the Kleinian or Duval or simple or Western double point. Probably some of the names.
You can use this.
Yeah, I have brought another eraser if it's better. I don't know if it's eraser, it's a problem. Otherwise, I have this spray. If you use a spray,
I think that's just about so. The Kleinian singularities. C2 over gamma, where gamma is a finite subgroup of S-factors. So, if you don't know about this classification of Kleinian singularities, I urge you to go and read a bit about it. This is sort of one of these amazing things. It's an appearance of the ADE diagrams in a place where you might not expect to find them. But these are classified by ADE diagrams, and in fact, you can do even better than that by the ADE thinking diagram. So the A ones are cyclic, and then the other ones are these binary dihedral or binary tetrahedral, etc. subgroups. So there's a classification, and for each one of these finite groups, the singularity that you obtain is a surface singularity. So we have 3 generators in single relation. These have been studied a huge amount, and this is a sort of family 2, or maybe the first, because I suppose these came before minimal singularity, and then you're going back to the 19th century, right? So
and these are in fact all of the 2-dimensional symplectic singularities.
yes, exactly. Yeah. Now, I just want to maybe hint at something, which is that we can extend to the full Dinkin classification. And this is according to Levy, so by considering Kleinians with a monodromy action. So e.g. G2 is a D4 singularity with an outer action of S3, right? That notion of monodromy does actually make sense, and I'll maybe mention the way that it makes sense later on when I talk about transverse spaces. But the point is that for each group of graph automorphisms of these diagrams, for each symmetric group of graph automorphisms, we get one of these diagrams, BCFG, and that's a one-to-one classification.
Right, this is also what's called folding, right? For Dinkin diagrams.
Yes.
Right? So
Yeah,
every non-simply laced Dinkin diagram is a folding of a simply laced one. And now geometrically, you're saying we can think about this folding operation as a monodromy. So if you're thinking like a family of the singularities of the simply laced type ADE with some monodromy.
yes, there are 2 dual notions of folding, and so this is one. And later on, when I talk about covers, you've got the dual. You need to replace each thing by its language dual. So we're going to see something like later.
I was just thinking naively of, a Dinkin diagram and an automorphism of the Dinkin diagram, such that if you take the fixed subspace of the cartan, you get the cartan for the folded.
Yes. So you need to take the language dual in order for this. For this, and I'll say in a bit. I'll say give you a reason to believe that.
Okay.
So you do it for finite or also for finite?
Right.
You can do this for affine as well, but then I'm not sure how to relate it to this two-dimensional symplectic singularities.
So there's an important subset of special nilpotent orbits. So the special orbits were defined in relation to the Springer correspondence. So the Springer correspondence is this correspondence that takes the geometry of the nilpotent current and churns out irreducible representations of the value. So it gives you a complete set of these irreducible representations. And among the irreducible representations, there are these special representations, which are defined combinatorially with two notions of degree that are equal. Now, it turns out that if you sort of reverse the Springer correspondence for the special representations, you get a subclass of the nilpotent orbits. Those are called special nilpotent orbits. You get trivial local systems of these orbits. These are the special nilpotent orbits. So they come purely from that sort of combinatorial data. But the weird thing is they have some geometry associated to them, which has some quite strong properties. And so that's the main thing that we're going to explore in the time that remains.
So when you use this definition using the Springer correspondence, it's a consequence that the Spalter-Stein map gives you special orbits for classical.
So it's a consequence that the
So if you take the Spalter-Stein map,
right,
and you use it to identify special orbits.
what's the Spalter-Stein map? Sorry.
So you take a partition of a classical and you compose it.
Yeah.
And
then you have some color.
Press it. Yeah.
Yeah.
So that's this is what I call the Spanish map. I don't know how you call it, but
So-
it is a way to compute special orbits, and somehow
So
you use the
so-
different definition.
So the way to think about that is that taking the transpose is something like mentioned by the same representation. You see it in the context of irreducible representation. So that should preserve the set of special representations. That's why that's one reason why you may hope that would work. Yeah, this is Okay, so you've actually introduced nicely one thing I was going to say. We have an important subset of the special nilpotent orbits. And so I'm going to write down the nilpotent orbits in SP6. So these come from partitions of 6, but only certain partitions of 6. Right, FD6, this is the symplectically algebra. And each odd part has to have even multiplicity. Right, so we can't have 5, 1. That would be a perfectly good partition of 6, but it doesn't come from the symplectic orbit for the symplectically algebra. So we skip the 5, 1, and 4, 2, 4, 1 squared, 3 squared. We can't have 3, 2, 1, so next one's 2 cubed, 2 plus 1 squared, 2, 1, 4, 4, 2. There's nothing says, if you go to the symplectically algebra, particularly nice, an orbit is coming from a partition lambda is special if and only if the transpose partition also comes from a symplectic orbit. I'm going to take the transpose. We think of this as a row of length 6. You just sort of reflect in the line y equal to minus x, and it gives you column of length 6, right? So the duals are 1 to the 6, This is 2 squared, 1 squared, 3, 1 cubed. This 2 cubed, 3 squared, 4, 2, 5, 1, 6. Right. So we can see that the ones that aren't good.
Last one is 6.
Sorry. Yes. Sorry.
So again, you said something important. You said, so first of all, for type A, I guess all of the orbits are special.
Yes, all the orbits are special.
And if we're in types B, C, D, then you're saying that an orbit is special if and only if the transpose is also
So for
special.
type C, yes. For types B and D, it's more complicated.
I see.
For type, I think it's okay for type B. For type D, it's definitely more complicated.
So for types B and C, you're saying it's equivalent to the transpose also being an orbit. That's what you're saying.
Yeah, exactly. So we can see there are 2 here where the transpose partition is not on this list here. That's this 3, 1 cubed, and this 5, 1. Everything else is okay. Right?
Can you say again with the right diagram?
I've just taken the transpose partition. So transpose partition. These are the symplectic partitions. So this is the nilpotent orbits in SP6. And all I've done is taken the transpose, and then I want to check whether the transpose partition I get here appears on the left-hand side. And in this case, it doesn't. 3, 1 cubed doesn't appear on the left-hand side, and 5, 1 doesn't either. All the others do. Right. So, so what we then obtain. So what we do now is we're going to basically sort of adjoin this orbit here to the one which is immediately opposed. And we're going to do the same thing with this here, right? And what do we mean by adjoin? So this union of these 2 orbits is going to be called a special piece, and the same thing down here. So if O is a special orbit, then the special piece P with O is equal to O bar minus, I've not left myself enough room, the union of all O prime strictly less than O special the closure of that unit. Right. So here we remove this, etc. So we've got everything else. The special pieces what is inside this green area. The same thing. So most of the special pieces are just a single orbit, right?
It could happen that an orbit is in more than one special piece.
So that's the next thing I was going to say is no orbit lies in more than one special piece.
I see. This is not obvious.
This can be.
So what we don't have is special. So that's big about, right? Okay, so okay, so in the simply laced cases, so A, D, and E. So for A, D, and E, the minimal orbit is special. But for the other types, that's not true. However, there does always exist a unique a minimal non-zero special orbit. So for B, C, and F4, the orbit of a short root element is the minimal special. And for G2, I'll draw a diagram in a few moments that will probably explain what's going on. Right, so I'm going to write here O min special. This equals O min if A B. Okay. But there's always that unique minimal special non-zero special orbit. Okay. So in this case, the minimal special is this one then.
And is the minimal special orbit closure normal then?
Yes.
Always.
In fact, that will follow from something that I'll say later. Okay, so here are some examples of interesting special pieces. Hopefully this won't take, writing these down won't take most of the last 20 minutes.
Well, we probably started a little bit late, so.
Right, so for example, for one, we've got G2. And there are 5 nilpotent orbits in G2. So I'm going to write them all down. That's not too difficult. Now at A1, that's the orbit of a long root element. A1 tilde is the orbit of a short root element. This G2A1 is the subregular orbit, so that's just a name for that. And this is the regular, right? This is the kind of Bonner-Carter notation. Okay, so the minimal special orbit for type G2 is the subregular. So in fact, you only have 3 special orbits: regular, subregular, and zero. I'm going to.
How useful is this Bonner-Carter notation?
How useful is it?
You use it all the time?
Yeah. Yeah. The G2 maybe is fine. Once you get to E8, you need some way of writing down there.
It's hard to, yeah. It doesn't really, well, to me, it doesn't reveal much of the property.
Yeah, I'll maybe try and answer that a bit later. I'll try and persuade you that it's important. Right. Okay, so we have 3 orbits inside the special piece. The second example is this is a sub-diagram of the F4 set of nilpotent orbits in F4. So I can remember this one, but it's quite a lot more complicated.
How many times have you had to write this in order to memorize it?
It has a structure for this.
This is F4. So that's a single special piece. Now, I'll write the orbit that comes underneath me. But the special piece is everything here, right? So there are 5 of them. And then the third example, I don't actually have space on the board. The third example is E807, E7A1. Okay, so there are 1, 2, 3, 4, 5, 6, 7 orbits in that. This is called the exceptional special piece in E8, the exceptional special piece in F4. Now, if you love your nilpotent orbits and then you know quite a lot of the Barr-Carter labels intimately, you know there's something really interesting about these two nilpotent orbits. So the fundamental group of a nilpotent orbit complete the fundamental group. Okay, so I need to slightly revise what I was going to say. So the fundamental group can be a bit bigger. So the fundamental group comes from the component group of the centralizer in the simply connected group. But let's not do that. Let's take the adjoint group, so you put it by the center, and look at the component group in the adjoint group of your nilpotent orbit. That component group is always either a product of S2s, or it's S3, or it's S4 once, and that's the once, or it's S5 one, that's the once, right? Okay, so and in these cases, it's also the fundamental group. So these special pieces are coming from orbits that have really interesting topological structure.
So say that again about the symmetric groups. What did you just say?
So the component group and the adjoint group is always either product of S2s or it's S3, and that happens.
Happens 2 times.
It happens in almost. It happens in the exceptional types. I think it maybe not in E6, but in all of the others. And S4 happens
How
once.
many S4? S4, but there is also other exception.
There might be maybe one of these has an S4. Yeah, I can't remember. I'm not sure. But S5 is definitely this one.
Just one.
It's certainly the only special orbit with an S4.
S5. So S4 happens once, you say, for F4, you say, and
So
S5
S4 happens once
for
in
F4.
F4. That's the
and S5 happens once, you say, for E8. And this is these are the pi 0 for the adjoint group.
Yeah.
Okay.
And if you like your numerical coincidences, there's something weird like this is the dimension of the orbit is the same as the dimension of a nil profile, no radical or something weird like that. So anyway, so there's lots of interesting stuff happens in relation to these nilpotent orbits that have interesting topology.
Oh, Danielle says for G2, F4, and E8, the adjoint is the simply connected. That's true, yes.
Yeah. The G2, F4, and E8, the central triple. Yeah. Okay, so I'm now going to write down.
Where is the again?
He's on my phone.
So I'm going to write down. So for
He's also
I'm going
somewhere.
to verbally give you some.
He's also somewhere, I suppose, maybe in
So-
Paris.
The phone is sufficient.
So Lustig was obviously interested in these special pieces and quite early in the
yeah.
history of this.
Yeah, I guess.
He conjectured that every special piece in any type is rationally smooth. So in other words, it has the same local cohomology as a smooth variety. And in classical types, Krafft and Procesi studied these partially ordered sets, the singularities associated to various of these pairs of nilpotent orbits. And they proved that each special piece in a later paper, that each special piece is in fact, is the quotient of a smooth variety by a finite group. So for classical types, Lustig's original conjecture was about rational smoothness. This was proved by proving a stronger result, which is that your special piece is the quotient of a smooth object by a finite group. And Lustig subsequently thought, well, that should be true in exceptional types as well. So we have this conjecture called Lustig's special pieces conjecture. Well, this is what we call it. You need to be able to distinguish the various conjectures that Lustig has made, right? So, yeah.
So the class,
This, is there a more geometric definition of this special feedback? This transpose, I don't have a picture in mind. Like, I understand what it is in terms of partitions, but
Well, that's precisely the special piece is the union of these two orbits, but then it's defined purely combinatorially. And so this is the thing that it has interesting geometric structure, but it just seems to come from nowhere.
But there are some things that one can say, right? I mean, you said that, is that right? That this was actually defined originally by representation theory. There was some notion of a special representation. Is that
Yeah, so that's
about? Was that
special-
where it originally came
Yeah, that's
from?
where it comes from, yeah.
And I don't know what it means for a representation to be special, but
It's just it's the file group, right?
right.
So there's these notions of generic degree and plate degree, so they need to be equal. So it's you just have this combinatorial data associated to these representations, and you read off the list of the ones for reasons I wouldn't be able to explain. These are kind of important in the representation theory of the associated file group, but at that stage it's quite difficult to see why this would have a geometric meaning.
Right, but this fact, so Yankee, but it is a good question. I mean, I didn't dare to ask myself, but somehow one thing that's happening here is that there is supposed to be, if I understood it right, going back at least to this BPLW papers, there's supposed to be some kind of a symplectic duality, and here symplectic duality is usually, we've discussed this before, it's supposed to usually reverse the Hasse diagram, but then this is supposed to be, in the case of nilpotent orbit closure, that this is supposed to be related to the Langland's dual and relating a orbit closure with a slice to some other orbit up on the opposite to it, the opposite position of the Hasse diagram for the Langland's dual. But now this turns out not to work as well as one might like, and so it turns out one of the fixes to that is to restrict to particular orbits for which it works better, which are called the special orbits, right? So there's actually some definition of special symplectic leaves, I think, or at least I'm not sure, I don't remember exactly, but from this paper, and that's supposed to correspond with the special orbits here, right? And they're supposed to have some particular behavior under the symplectic duality, right? It's supposed to be a bijection of symplectic leaves and symplectic leaves of the special symplectic leaves and special symplectic leaves of the dual that reverses the poset.
Yeah.
Is that right?
You're right. That's maybe one way of thinking about
And they're
it.
called special, I guess, because it seems that it's supposed to generalize what happens in the case of special orbits, which were defined by representation theory. Is that right?
There's special representation, so it comes directly from it's borrowed directly from the.
Right, but basically they figure out what happens geometrically there, and then they say that actually this is supposed to be part of a more general phenomenon in the situation of symplectic dual, symplectic singularities, right?
so there is a notion of splitting this in like fixed branches and long branches and so on as well.
Yes, I think so, yes. So basically, when you have a symplectic singularity, so I don't know, like they had their conical symplectic singularity. I don't know if they needed to be conical or whatever, but they take a symplectic singularity, they have this notion of, from the quantization of special, and it's supposed to have the coincide in this case with special orbits.
So we have explicit quibbles for the first two cases of G2 and 4, but we don't have for written ones. I hope that this will be found sometime.
Sorry, we don't have.
So he was asking about this duality in terms of X function. So we have explicit quibbles for the case of G2 and for the case of F4, but we don't have it for the case of F4.
So I think it's translated into what I think Bianchi was talking about. In mathematics, now we have these definitions of Higgs and Coulomb branch of a pair of a reductive group and its representation. And so I guess what you're saying, Amihai, is that Dia's in exceptional types, these special, even special or not, these nilpotent orbit closures do not necessarily appear in that way. Right? But maybe there's a more general thing you can call a gauge theory that it's a Higgs or Coulomb branch of, that you want to understand. Is that it?
Well, for the case of F4, the quiver contains symplectic anatomy. Whereas for the case of G2, the quiver contains a loop.
I see. So in the G4 and F4 case, actually, these are what, Higgs or Coulomb branch of some gauge theory.
Very explicit quiver.
A very explicit quiver. So it's not even just a reductive group in a representation, but one that's given by a specific kind of quiver graph. But in the E8 case, is it not known then whether there's even a pair of a reductive group in its representation such that Higgs or Coulomb branch gives you this
It's very
orbit
difficult to
closure?
understand. We try, we keep on trying.
So physicists also, as I understood it, have a more general notion of a gauge theory, which doesn't have to come from a pair of a reductive group in its representation, but these quivers are only very special cases of group and representation.
Oh, thank you.
Right. Okay, so just in the last few minutes, I can state the.
Yeah, take your time. Sorry, we interrupted you a lot, so you
Yeah,
can.
I've got. Yeah. I want to get to the highlight. So the highlight is not quite, well, this is the special pieces conjecture. So the statement is that every special piece, the union of these three orbits, the union of these five, the union of these seven, is so essentially sort of directly based on the result of changing the special for classical algebras. That each of these special pieces should be quotient of a smooth variety by a finite group gamma, and gamma is given explicitly. It's something like fundamental group. In each of these cases, it is exactly the fundamental group of the.
This is the so-called
spectral orbit.
A bar O, right? A bar O.
A bar O, yeah, yeah. So it's a little bit technical. So there's something called Lussig's canonical quotient. I think that's A bar O. This is a subgroup of that, but usually it's equal to it. But
I see.
Eric Summers would be able to clarify. Yeah.
But he's not here. Only Danielle is here. So
You raised earlier the distinction between an orbit that was normal and an orbit that wasn't.
Yeah.
Is this statement true about the orbits or about the normalization?
This is
normalization.
so each of the automatically the quotient of a smooth variety by a finite group is normal. So a consequence of this is that P of O is normal, but the failure of normality is generally it's only expected to occur for non-special orbits. So the normality problem isn't fully solved.
So, but in that F4 case, so there was orbits in that special piece on normal.
Yes, true, but the closure of this thing at the top is normal.
Oh, yes.
So that's all that matters. Yeah. You're absolutely right. The failure of normality can be seen exactly in the version of failure.
So this is.
So in a moment, I'll say that our result is slightly weaker.
it could happen in spite of this conjecture, right? It could happen that the entire closure of the special orbit is not normal. This is only saying that the special piece is normal, right? But you're saying it's the whole closure.
The consequence of this result would be special piece.
Right, the special piece. But then you could ask whether the whole closure is normal, right? When you're saying this, were you saying that is true?
So how is the special piece different from the closure of the orbit at the top?
You've removed some part. So
You removed
the
other
closure might
special
be
pieces.
non-normal somewhere further down.
Oh, I see. So it's the union of those orbits.
Yeah.
Is normal.
Exactly. It's just those orbits. So for example, you've removed this. Yeah. So
I see. So it could happen actually that the entire closure is not
I
normal.
think all special orbits are expected to be normal, but it's not known. So
I see, okay.
In attempt to prove.
Oh, I see. But you don't need that. You just need
we don't end up
the piece to be normal. Okay.
So normality is some law coordination issue, right? So That means the orbits that you're removing are quite big.
No, you can have it. They can be non-normal and quite.
In a very
Yeah, in the large dimension. So in the classical types, failure of normality always happens in dimension 2.
Right.
It's always branched non-normalities. So for exceptional types, that's not true. So there are there's much more weird and wonderful examples of failure of normality.
You can have unibranch, but not normal singularities.
Yeah, exactly. Yeah, yes. And also that could be normal in dimension 2, 4, 6, but then we know that they're not normal further down. So, yeah. But it's not solved, right? So there's a list of known non-normal orbit closures, and it's conjectured to be a complete list. And
You made the list, right, of all of the non-normal slices and exceptions, right?
sorry,
You have a list of the all types of non-normal slices, an exception of that.
we have a list of non-normal slices for what we call minimal degenerations, for adjacent variables. Yes, but yeah, that's classified. Yeah, I think we did manage to completely solve that. There might be 1 or 2 cases in type E8 where we're not sure. We only have results of normalization, but that doesn't solve the normality problem, right? You could have an orbit closure which is non-normal, which which further down. Okay, right. So
Sorry, so you were saying that and then classical types, it's always when you're not normal, it's always because there's a not normal codimension 2 slice to a codimension 2 to 2-dimensional slice to a codimension 2 sub orbit.
exactly, yeah.
But that doesn't mean that you couldn't have, and it's at the minimal. It's like is that the
Yes, it's always
everything else is below that one in this case, or
where you can have
could you have multiple?
you could have 2 edges and one of them ends up being non-normal, but the other side is.
I see, but all of the non-normal stuff happens underneath a codimension 2. I see, but in exceptional types, how big can that codimension be? You were saying 8 or something like that?
So at least 6,
Okay,
because we have an example of a branched non-normality.
6,
I'd have
and
to
then
check.
the normalization of this minimal slice is C6.
In which
E8. So you're saying in E8 there is a minimal slice which is not normal of dimension 6.
is branched, and so the slice is two minimal singularities type G2.
You see.
So 6-dimensional. So the normalization would just split those. Yeah.
so I have some comments from Daniel that I neglected to tell us, but so here he's saying that in classical, non-normality can be seen in codimension 2 with 2 branches, is what you were saying.
Yeah, so it's like I said, full.
Right, with 2 branches, yeah.
Yeah.
And he said that it should always be a subgroup of the canonical quotient, but in almost all cases, in exceptional types, it's the whole group. I guess this is basically what you said.
Yeah, exactly. Yeah.
Yeah.
Okay, right. So I need to just say a little bit about transverse slices.
Sorry. This gamma is a subgroup of A bar. Right?
Yeah, so gamma is usually what's called a bar of so I mean it's usually even the component group of the orbit, but this a bar O is some
So in what cases they are different?
Sorry?
In what cases gamma and A bar O are different?
There's a short list. I can't remember exactly which ones, but I mean the content of the conjectures is, you know, this is really only difficult when gamma is a larger group, right? So I'll just point out the gamma is S3 here, and the orbits, which are the strata, they correspond to the parabolic subgroups of S3. And then here gamma is S4. We've got the same diagram again. And here we've got the parabolic subgroups of S5. So most of the work involved in understanding this is gamma is equal to the component group, or maybe to this quotient that plus the components of the component group.
See, here I will be able to tell you B2 is sigma 2 squared or B2 is sigma 3. You have this choice.
So if B2 is, so the geometry is different. But so here it's not so easy to see. Like the geometry does not distinguish with an S4 and an S3, S2, and these are all basically the same. So see. So I think it's not really possible to, if I remember correctly, it's not possible to distinguish them. But you can read, so Lustig has a very specific, he doesn't just conjecture the group, he says which orbits correspond to which parabolic subgroups of gamma. So, okay. Turn to the slide. So just a very quick sort of motivational introduction. So the geometry of a nilpotent orbit closure is complicated. It contains, for example, the information about the partial order of all of the orbits in the loop. Okay, so what you can do to simplify this is to consider instead a pair of orbits, one less than the other. Then the transverse slice gives you an understanding of the geometry of this closure close to a point of no place. So solid slice. It's a transverse slice, and in V algebras we usually take Slavy slice. So the Slavy slice at an F in O prime is F plus the centralizer, where H the F is SL2. So, and the point is that the geometry of this F is in the smaller orbit, so the geometry of O bar in an analytic neighborhood of F is determined by let's call this X intersected with O, right? And so the notation that was introduced by Kraft and Chase is something like this. This tells you singularity of type of O bar in closure here in the neighborhood of a plane to O plane. And so you have a smooth equivalence class of these things, and what you're really interested in is the equivalence class of these singularities. This is isolated.
So Danielle has told us from Lustig notes on unipotent classes It says that AC equals GC, except if C is the class of type E8, B6, when AC equals S3 and GC equals S2. You can interpret that.
Well, he answers the question.
Yeah, sure, but I think that's the distinction between the canonical quotient and algebra.
Right.
And then you need to know what the canonical quotient is, I think.
Right. Okay, yeah. So that's the exception, right? Where it's not the whole group. Type E8, B6, when AC is S3 and GC is S2. So you're saying there's only one exception then, where it's different. It's E8 parentheses.
We need to go over each one of them separately. That's later.
Yeah.
Okay, so I've managed to get as far as, so these slices are determining the geometry. And so this slice S, it's going to pass through all of the orbits intermediate between alpha and beta, right? And the dimension of this intersection will be equal to the dimension of the dimension of your intermediate orbit minus the dimension of O prime, right? These slices are really kind of telling you a lot about the geometry of these local analytic neighborhoods. So here's the theorem which we were hoping would be on the archive by today, but that deadline is always slip. I don't think I've ever met a deadline.
Well, can't you get an extension because we're having you give a talk here?
Yeah. So here's the theorem. So let's O be special. And then I can't remember whether I said that there always exists a unique minimal orbit in the special piece.
Yeah, you didn't say.
Right. Then F as above. Let me denote that as F. And F in O primes.
By the way, what is this letter for the slaughtery slice? What is that?
It's an S.
That's an S, okay. S for slaughtery or S for slice? Okay.
Yes.
It says the subgroup they're interested in is not GC, but it's G prime C. Okay. Well, maybe I will tell you this later.
Right, I want to leave some stuff. I think I'm gonna remove what's above. Does Daniel disagree? Right.
Disagree with what?
I didn't quite hear what.
Oh, he was explaining more. So they had this. Lustig was saying when AC equals GC, because actually the subgroup you need is not GC but G prime C.
Yeah.
And says in more detail about that.
Okay.
But he said I shouldn't interrupt you, so.
So here. Right. Okay. So the result is a kind of a, we describe it as a local version of the special piece conjecture. Right. Local version meaning this conjecture says there exists a global object which you quotient by gamma, you get your special piece. And what we're doing is taking a slice inside the special piece and saying that slice is equal to the quotient of a smooth thing. Well, what's the most natural smooth thing you could take? That's a vector space by the same group gamma. And in fact, H is
H plus H star to the power K.
Okay.
yeah, that's just to emphasize the symplectic structure. In fact, they're isomorphic as modules are. same. So this is the contents of algebra.
And what is K?
Yeah. Okay. Oh, that's right?
Yes.
So K is if n is greater than 2, then K is equal to 1 with one exception. I'm going to give you the Barlow-Carter label with that one exception, just to show you how Barlow-Carter label is going to be useful, right? That's one exception is when K is equal to 1. So note that what we're dealing with then is n is equal to 3.
In which algebra is this?
Sorry?
This orbit, in which algebra?
What's the?
D41, in which algebra is it?
Oh, sorry, in EX, yeah. So in this case, you've got an 8-dimensional vector space over S3. But otherwise, when n is 2, what is this? This is just a vector space over S2. And this is the same thing as a type C minimal singularity. But for n greater than 2, this is where the special pieces of conjecture becomes hardest. There's this one case where K is equal to 1, otherwise it's just H plus H star over Sn. These are sort of nice examples of symplectic singularities which have one of these things called symplectic resolutions. But when K is 2, you don't have a symplectic resolution. So in fact, we've got an interesting case of one of these orbits doesn't have a symplectic resolution. This becomes a terminal singularity because the singular locus is co-dimension forward. Okay, so this is the local version of the special pieces conjecture. So what about the global version? So I'm just going to very briefly, since I have relaxed, but it is kind of lunchtime. So I'm just going to ramble very slightly about what happens next. So this result will appear on the archive. So the question of how to go from here to the global version is a bit fraught. So many years ago, really more than comfortable with, we thought we were kind of approaching a proof. And I think there was a misunderstanding between some of us. And one of the members of the team, I won't say which one, essentially kind of announced a proof of the special pieces conjecture in a conference with lots of people, including Lustig present. So, but it wasn't as simple as that. However, we're now pretty much certain we have the right path from here to the global version. And what is the path? So the path is to take your special orbit O, and there's a very standard way of constructing, or sometimes called the affinized universal cover of that orbit. So you can come up with to construct the universal cover, there's a natural way of doing that. But then you have an affine version of it, which just comes from taking the spec of the coordinate ring, right? And your O bar is, or at least the normalization of O bar, is a quotient of that thing by the group M. Okay, so all we want to know is that affinized universal cover is smooth above this slice. So that's kind of, that sounds easy, right? A priori, there's no reason to tell you that the pre-image wouldn't be, n factorial copies of this singularity. What you want is the pre-image to be H plus H star. Okay. The pre-image in the universal cover. And that's the thing that we are fairly sure that we can do using a concrete description of the model for the universal cover and some computational results from the tricky case. I'll stop there. There's plenty more I could talk about. I didn't actually cover the abstract, but I'll show you that before the finish.
So Danielle said that this was the statement for the exceptional groups, and then the classical groups, it has to take a product or something. I didn't understand his.
Yeah,
comment.
so this is just for exceptional types. Sorry, it should be special in the exceptional types. Thanks, Danielle. So for the classical types, you can have a product of S2 to but for the exceptional types, it's always an S8.
Okay.
So this is only open, you know, the conjecture, the piece of conjecture is only open in exceptional types.
I see. And in particular, the statement you get with this product in the classical types follows from what's known in classical types.
Yeah, so I think we are likely to just sort of maybe sort of re-verify that statement, but after the
But if you take
In,
how they verified it, does it imply your statement in that
when they
case?
were proving equivalences of various sort of singularities in classical types,
Mhm.
they did this by sort of lifting. They had this orthosymplectic case where you would lift to some object Z and then project down in the other direction. And the point is that Z ultimately becomes the smooth object that you're quotienting by when you,
Mhm.
yeah. So it just popped out of their construction.
So maybe they don't make this statement there, but that follows from what
They
they.
did make a statement that it's a quotient of. I don't think they checked that gamma was the right gamma.
Right.
But they did make the statement that it's a quotient.
And the statement about the Slotowee slice as well, I guess.
Yeah, it's a fairly.
Okay. But you can prove
So
this.
I think that direction is not. Yeah, it's not.
But you can prove this without having to use their construction, is what you're saying.
Yeah.
In the classical types.
Yeah, we can sort of do. Yeah, we can sort of go in the other direction. Yeah.
Okay.
So I'll just try and concretize your theorem. So if you go to the F4 example,
Yeah.
You've got you have a minimal orbit in respect of these. That's your A2 with A1.
Yeah.
And then you can take slices from there up to any of the other orbits in the spectral piece.
Yeah.
And there'll be different things. And your basically your formula is saying that those different things are this space divided by the finite.
So that it says the slice from here up to there, the whole thing.
Yeah.
Is this object. Obviously, you can restrict the quotient to some.
And what would it be if you took the slice up to C3A1?
Up to this one.
Yeah.
So
it doesn't say.
so it's a bit. Let me just sort of think, because it's still a quotient, but what's complicated is, so for example, you're looking at C3 plus C3, but really you should think of this as traceless matrices, right? A plus B plus B, then SCU minus C plus B plus U, right? So those are your pairs, right? Now, generically, the stabilizer of this pair is trivial, in S4 is trivial. So this C3A1 is the image in the quotient of everything which is fixed by an S2. Now you have choice over which S2 that is. But let's take the S2 which swaps the first two. So the S2 fixed point would give you pairs A, C minus 2A plus C, S, S, U minus 2S plus U. Right, so the set of all these pairs, the image of those in the quotient will give you this. But this, of course, this is not stable under the action of S4. You need to take the union of this with all of the other, the ones where the first entry is in the third entry and the first thing in the fourth. So you actually get 6 different irreducible, just subspaces, right? 6 different subspaces. Once you take the union of those, you can function by the S4 action, but it's a bit of a.
So you're saying primarily relates to the bottom orbit and top orbit, and
Yeah,
special ones.
Yeah.
You could solve it as symmetric 4 of C2.
Symmetric for C2.
That
That seems so from the action. Yeah, so that's right. I'm just thinking about the coordinating of that thing. Why am I uncomfortable with that? Yeah, so. Yeah. Yeah, exactly. So it's like, yeah, if you take a pair of vectors, U, V, it's, okay. Okay,
And that they should be general, but in other places as well.
Yeah.
It will be symmetric product of some.
Yeah. Depending on age.
But
being self-dual.
symmetric power 4 of C2, isn't that 5 dimensional?
There's a trivial one that you remove.
Other questions? I guess Danielle doesn't have any questions. He just came to answer questions. Great. Well, let's thank Paul again then. And we'll have lunch then. So after lunch, and well, we could also go somewhere that's less hot, I suppose, if we find somewhere. So we can try the physics room maybe, or otherwise with my office.
No
That's hot.
ventilation.
No ventilation.
Here the reason was the ventilation. But that's the 503. You refer to the problem with the common room is that once you have more than 5 people, because of the non-ventilation, it's hotter, but it doesn't cool.
Okay, well, I do have this room reserved, so if we want to come back here, if that's better, then we can just come back here. So let's take our lunch here then. But let's say goodbye to Danielle because I have to take my phone with me. So
Bye, Danielle.
bye, Danielle. Au revoir.
Bye.